What if everything we think we know about the universe is just the tip of the iceberg? Picture this: you're staring up at the night sky, counting stars. But what if there's an entire dimension of reality hiding just beyond your perception, invisible to the naked eye, untouched by our most advanced telescopes? The truth is, the cosmos might be far stranger than we've ever dared to imagine. Scientists and philosophers have spent centuries unraveling its secrets, and yet, the deeper we dig, the more we realize how much we don't know. Hidden dimensions, parallel realities, layers of existence folded into the fabric of space-time like pages in a book we can't quite open. These aren't just ideas ripped from science fiction. They're serious theories backed by cutting-edge physics and mathematics, hinting at a universe far more complex and bewildering than our everyday senses can grasp. That's where these 30 theories about the universe's hidden dimensions of thought come in. Think of them as 30 different keys, each one unlocking a door to a new way of seeing reality. Some suggest that extra dimensions could be curled up so tightly we'll never perceive them directly, while others propose that our entire universe is just one bubble in an infinite cosmic foam, bumping against others we can't see. And then there are the wilder ideas that consciousness itself might be a dimension, or that time doesn't flow in just one direction but branches infinitely, like a river splitting into countless streams. These aren't just abstract concepts. They could reshape everything from how we understand gravity to the very nature of existence itself. So why does this matter to you? Because hidden dimensions aren't just for physicists, they're clues to the biggest questions we've ever asked. What's out there? Are we alone? Is there more to life than what we see? This journey through the universe's best-kept secrets isn't just about science. It's about expanding the limits of what we believe is possible. And by the time we're done, you might just see the world and your place in it in a whole new light. So buckle up, we're about to dive into the unknown. The first theory that could rewrite our understanding of reality is the holographic principle, an idea so mind-bending it suggests our entire three-dimensional universe might be nothing more than a projection, like an intricate cosmic illusion. Imagine a hologram. When you look at that shimmering image floating in midair, every angle, every depth you perceive is actually encoded on a flat, two-dimensional surface. Now take that concept and stretch it to the scale of the cosmos. Physicists like Leonard Susskind proposed that all the information describing everything in our universe, every galaxy, every atom, even your thoughts, could be stored on a distant, two-dimensional boundary, like some unimaginable celestial hard drive. What does this mean for us? If true, it would imply that the solid, tangible world we experience, the feeling of grass under your feet, the weight of a book in your hands, is just an incredibly convincing projection. Reality, in this view, becomes a kind of cosmic sleight of hand, where depth and dimension are an emergent property of something far simpler. The implications ripple outward, touching everything from black holes to the nature of consciousness itself. Some researchers even speculate that if the universe is holographic, our perception of free will or individuality might be part of the illusion, like characters in a video game unaware they're made of code. But how could this possibly work? Think of it like a movie. The images on screen seem to move and breathe, but in reality, they're just a rapid sequence of still frames, a trick of the mind that creates the illusion of motion. The holographic principle suggests space-time might operate similarly, with our brains stitching together a seamless experience from underlying data we can't directly access. Even gravity, the force that shapes the cosmos, might not be fundamental at all, but rather a side effect of how information is translated from that hidden two-dimensional surface. This isn't just wild speculation. The math behind black holes, where the amount of information inside seems fundamentally linked to their surface area, hints that the universe might really work this way. It raises haunting questions. If we're living in a hologram, who or what is the projector? And if consciousness emerges from this grand illusion, could altering the code change reality itself? The holographic principle doesn't just challenge what we see, it forces us to ask whether seeing, in the way we understand it, is even real at all. What if everything around you, the screen you're staring at, the air in your lungs, even the thoughts forming in your mind, was nothing but lines of code in an unfathomably advanced simulation? This is the simulation hypothesis, a theory that sounds ripped straight from a sci-fi movie, but has gained startling credibility among philosophers and tech billionaires alike. At its core, it suggests that our entire universe might be an artificial construct, an immersive virtual reality created by some higher form of intelligence. Philosopher Nick Bostrom framed this idea as a trilemma, three unsettling possibilities, at least one of which must be true. Either civilizations always go extinct before developing simulation technology, they choose not to simulate entire universes, or we are almost certainly living in one right now. The logic is hauntingly simple. If even one civilization reaches the capability to create hyper-realistic simulations, they could generate countless virtual worlds, making simulated beings vastly outnumber real ones. The odds, statistically speaking, tilt overwhelmingly toward us being among the simulated. Elon Musk famously echoed this view, arguing that the rapid advancement of our own virtual reality and video game tech hints at a future where indistinguishable simulations are inevitable. If that's true, he posits, the chance we're in the original, base reality is astronomically slim, maybe 1 in billions. But it's not just futurists leaning into this idea. Quantum physics throws its own curveballs. Phenomena like the observer effect, where particles behave differently when measured, eerily resemble how a video game might render graphics only when a player looks. Even the pixelated nature of space-time at the tiniest scales, where reality appears grained, could suggest a built-in resolution limit, like the blocky edges of an overstretched digital image. Critics push back, of course. Some argue that simulating every atom in a universe would require more energy than the universe itself contains, unless the simulation skimps on processing power when no one's looking. Others point out that consciousness, that elusive spark of self-awareness, might be impossible to replicate with mere code. But then again, how would we know? If the simulation is flawless, every argument against it could just be part of the programming, making doubt itself a feature rather than a bug. Here's where it gets spine-tingling. If we are in a simulation, the creators might be simulations too, nested inside deeper layers like cosmic Russian dolls. Or worse, what if they're running millions of versions of us, tweaking variables to study outcomes? It reshapes existential questions. Is free will just an algorithm? Is death a shutdown command? And if we ever proved this was a simulation, would the admins hit the reset button? The simulation hypothesis doesn't just question reality, it turns the act of questioning into the ultimate glitch in the system. Now let's venture into one of the most dizzying theories of them all, the many worlds interpretation of quantum mechanics. Forget parallel universes existing light years away. This idea suggests they're being created right here, right now, with every choice you make. Picture this: you're standing at a crossroads deciding whether to turn left or right. In our everyday experience, you pick one path and move forward. But according to many worlds, the universe doesn't just follow your chosen route, it splits into two separate realities, one where you went left, another where you went right, each just as real as the other. This isn't science fiction. It's a legitimate interpretation of quantum theory, first proposed by physicist Hugh Everett in the 1950s. The math behind it comes from the same equations that govern particles at the smallest scales, where things behave in ways that defy common sense. Take Schrödinger's famous cat, a thought experiment where a feline in a box is simultaneously alive and dead until someone opens the box and looks. In the many worlds view, the cat doesn't hover in a ghostly state between life and death. Instead, the universe splits. In one branch the cat lives, in another it dies. Both outcomes happen just in separate, non-interacting timelines, but why stop at cats? Every quantum event, every flicker of an electron, every random decay of an atom could spawn new branches. Your life isn't a single thread, but an ever-expanding tapestry of realities where every possibility plays out. Missed a flight somewhere, a version of you caught it, flipped a coin, there's a universe where it landed on the opposite side. The implications are staggering. Regret might be an illusion because somewhere every road not taken is being traveled. Critics argue this is extravagant. Why conjure countless unseen worlds when one universe seems enough? But supporters counter that many worlds actually simplifies quantum theory by removing the need for wave functions to collapse into a single outcome. There's no mysterious observer effect. Instead, all outcomes exist just in branching realities. The eerie part, we'd never know. These parallel worlds are like shadows cast by our own, forever out of reach. What's wildest is how personal this gets. The person you are today is just one thread in an infinite tapestry of versions, each shaped by different choices. Ever wondered what if, according to many worlds, those alternate lives aren't fantasies, they're real, unfolding in universes so close yet forever separate? It's a humbling thought. Every moment is a fork in the road, and somewhere every path is being walked. What if our universe is just one sheet of reality floating in an endless cosmic ocean, bumping against others like invisible ships in the night? This is the brane multiverse theory, a mind-stretching idea that reimagines our cosmos as a three-dimensional brain adrift in a higher dimensional space. The term comes from membrane, and the concept emerges from string theory, that grand attempt to unify all forces of nature. According to physicists like Lisa Randall, these branes could be everywhere, stacked or drifting through dimensions we can't perceive, each hosting its own separate universe with its own laws of physics. Here's where it gets wild. Imagine our universe as a slice of bread in an infinite loaf. The other slice's parallel branes might be centimeters away in a higher dimension, but we'd never know because everything we experience, from light to gravity, is trapped on our own brain. Except perhaps for gravity. Some models suggest gravity leaks between branes, which could explain why it's so weak compared to other forces. Think of it like a soundproof wall between hotel rooms. You wouldn't hear the neighbors talking, but if someone stomped hard enough, you might feel the vibration. That faint tremor could be gravity's footprint from a neighboring universe. Then there's the collision scenario. If branes occasionally smash together, the energy released might spark new Big Bangs, cycling universes into existence like bubbles in a boiling pot. This isn't pure speculation. The ekpyrotic universe model, developed by Randall and Raman Sundram, proposes that our cosmic beginning wasn't a singular explosion but a violent brane collision. The afterglow we call the cosmic microwave background could even carry scars from that primordial crash. String theory ties it all together. In this framework, the fundamental particles aren't dots but tiny vibrating strings, and their harmonies dictate the laws of physics. Those strings might be anchored to our brain, explaining why we're stuck here. But if higher dimensions exist, there could be strings stretching between branes like puppet strings, orchestrating realities we can't fathom. What does this mean for us? If true, there might be entire worlds inches away in a direction we can't point to, their stars and civilizations forever out of reach. Or worse, what if a collision is overdue? The brane multiverse doesn't just expand our idea of space. It turns the cosmos into a hall of mirrors where every reflection might be another universe just beyond the glass. What if the Big Bang wasn't the beginning of everything, just one heartbeat in an endless cosmic cycle of death and rebirth? The cyclic universe theory turns our linear view of time on its head, suggesting that the cosmos doesn't have a single origin or final fate. Instead, it pulses like a vast, breathing organism, expanding and contracting in an infinite loop. At the heart of this idea is renowned physicist Roger Penrose, whose conformal cyclic cosmology paints a picture so grand it makes the traditional Big Bang seem like a single act in an eternal play. Picture the universe not with a definitive start, but as a series of chapters where each one, called an eon, begins with a Big Bang and ends in a heat death so complete that time itself loses meaning. But here's the twist: when the universe stretches into an endless, featureless void, Penrose suggests it becomes mathematically indistinguishable from the conditions of a new Big Bang. It's like erasing a chalkboard so thoroughly that the next scribble looks like the first stroke all over again. The cycle resets and a new eon dawns, carrying faint echoes of the past in the form of gravitational ripples Penrose calls Hawking points, remnants of ancient black holes from universes long gone. This stands in stark contrast to the classic Big Bang model, where time, space, and all matter burst into existence from a singularity and race outward forever, destined to fade into cold, empty darkness. The cyclic view offers something hauntingly poetic: no true end, just transformation; no absolute beginning, just renewal. It's the difference between watching a candle burn down to nothing and realizing the wax can be melted and remolded into a new flame. But how could a dead universe spark back to life? Penrose's math hinges on the idea that at extreme scales, particles lose their mass, a concept called conformal symmetry, allowing the ashes of one era to become the kindling for the next. There's no need for mysterious dark energy or cosmic contractions. The cycle emerges from the sheer geometry of spacetime itself. Skeptics argue this stretches physics beyond recognizability, but supporters point to tantalizing patterns in the cosmic microwave background, circular anomalies that might be scars from black hole collisions in previous eons. The implications are staggering. If the universe is cyclic, everything we see, every star, every life form, might be a recurring motif in an infinite symphony. Civilizations could rise and fall countlessly, their histories erased by each reset, their triumphs and tragedies doomed to repeat in variations we'll never witness. It's a humbling thought. Our entire existence might just be one verse in a song the cosmos has been singing forever. Here's a thought so unsettling it might keep you up at night. What if you, the person reading these words right now, aren't actually a human being with years of memories, but just a flicker of consciousness that blinked into existence a moment ago, floating alone in the void? This is the Boltzmann brain paradox, a cosmic horror story written not by fiction writers but by the cold equations of thermodynamics. It comes from a simple question: in an infinite universe governed by entropy, how likely is it that complex structures like brains could form purely by random chance? The idea traces back to physicist Ludwig Boltzmann, who grappled with how order emerges from chaos. His work revealed that even in a vast, disordered universe, tiny pockets of order can randomly appear. Given enough time, and we're talking timescales so long they make the age of our universe seem like a heartbeat, statistics demand that a fully formed, self-aware brain could spontaneously assemble from the quantum foam, complete with fabricated memories of a past that never happened. Picture a snowflake crystallizing in a blizzard, but instead of ice, it's a thinking, feeling mind, convinced it's lived a full life when in reality, it's a temporary glitch in the cosmic noise. This isn't just a philosophical nightmare, it threatens the foundations of cosmology. If Boltzmann brains are more probable than real, evolved beings like us, because creating one mind requires far less energy than crafting an entire universe, then statistically, you're far more likely to be a Boltzmann brain hallucinating reality than an actual person. Every memory, every sensation, even this sentence you're reading could be an illusion conjured by a disembodied brain that formed and vanished in an instant. Scientists have wrestled with ways to dodge this paradox. Some argue that certain cosmological models, like an eternally inflating multiverse, might make genuine observers like us more likely than Boltzmann flukes. Others suggest the universe's arrow of time, the irreversible flow from order to disorder, acts as a safeguard, preventing such random consciousness from arising. But the haunting counterpoint remains. How do you prove you're not one? Any test you devise, any evidence you gather, could just be part of the hallucination. The paradox forces us to confront the fragile nature of reality. If existence can be faked by thermodynamics, does that make our experiences less meaningful? Or does it underscore how astonishing it is that we're here at all? The Boltzmann brain might be the ultimate skeptic's trap, a thought experiment where even doubt becomes untrustworthy. After all, if you're just a momentary spark in the dark, how would you ever know? Imagine falling into a black hole, the ultimate point of no return, where gravity warps time and space beyond recognition. Now, what if we never actually left? The black hole universe theory turns this terrifying scenario into a cosmic blueprint, suggesting that our entire universe might exist inside one. This isn't just a wild thought experiment. It's a serious hypothesis that bridges the gap between black hole physics and cosmology, proposing that every black hole could birth a new universe inside it, with its own laws of physics and even its own black holes nesting further realities within. At the heart of this idea lies the strangeness of singularities, those infinitely dense points at the center of black holes where our understanding of physics breaks down. Some theorists, like physicist Lee Smolin, argue that when matter collapses into a singularity, the conditions might be just right for a new universe to bubble into existence, hidden behind the event horizon. Think of it like a cosmic Russian doll. Our universe could be nested inside a black hole from a parent universe, which itself might be inside an even older black hole, stretching back in an endless chain. Smolin takes this further with his theory of cosmological natural selection. It's a Darwinian twist on the cosmos. Universes that produce more black holes reproduce more often, creating offspring universes with slightly tweaked physical constants. Over countless generations, universes fine-tune themselves to maximize black hole production, explaining why our own universe seems oddly hospitable to life. After all, if black holes are cosmic wombs, a universe that makes plenty of them would dominate the multiverse landscape. The math behind this is mind-bending. When a black hole forms, the extreme warping of spacetime near the singularity could theoretically create an entirely new spacetime continuum, disconnected from our own. From our perspective, anything crossing the event horizon is lost forever. But from the inside, that infalling material might become the seeds of a new cosmos. It's like stepping through a doorway that, from the outside, looks like a one-way exit, but from the inside opens into an infinite hallway. Critics question how information could pass between these layers, but some models suggest that the quantum data scrambled in a black hole's radiation might encode the blueprint for its offspring universe. Others argue that if black holes spawn universes, we should see traces of their parent in our cosmic background, an imprint of the greater reality we're hidden within. The implications are staggering. If true, black holes aren't just cosmic vacuum cleaners, they're creators, birthing new realities with each collapse. Our universe's expansion might even be the afterglow of some primordial singularity's explosion. It redefines eternity, not as an unbroken timeline, but as an infinite cascade of universes being born, dying, and regenerating through black holes. Suddenly, the darkest objects in the sky become the brightest sparks of cosmic renewal. What if consciousness isn't something the brain produces, but something the universe is made of? This is the radical premise of panpsychism, a theory that turns our understanding of reality inside out. Instead of treating consciousness as a latecomer in the cosmic story, emerging from complex chemistry in living brains, panpsychism suggests it's been here all along, woven into the fabric of existence itself. Think of it like this: just as gravity is a fundamental force present everywhere from falling apples to orbiting planets, consciousness might be a basic feature of reality, humming beneath the surface of everything from electrons to galaxies. Philosopher Galen Strawson argues that consciousness can't just pop into existence out of unfeeling matter. How could billions of unconscious atoms suddenly create the vivid experience of a sunset or the sting of pain? To him, the only logical solution is that some form of experience, even if incredibly simple, exists at the most basic levels of reality. It's not that rocks are pondering philosophy, but rather that the raw ingredients of sensation might be as universal as mass or charge. This isn't mysticism, it's a serious attempt to solve the hard problem of consciousness, the puzzle of how subjective experience arises from objective physics. Quantum mechanics adds tantalizing weight to this idea. At the subatomic level, particles behave differently when observed, as if awareness itself influences reality. The famous double-slit experiment shows electrons acting like waves until someone measures them, at which point they choose a definite state. Some theorists, like Nobel laureate Roger Penrose, speculate this collapse might hint at proto-consciousness in matter itself. If even particles have a whisper of experience, then human consciousness could be those whispers amplified over billions of years of evolution, like rivers merging into an ocean of awareness. Critics dismiss panpsychism as poetic nonsense. How can an electron feel anything? But supporters counter that denying consciousness to fundamental reality leaves us with an even bigger mystery: how to conjure it from nothing. Panpsychism offers elegance, suggesting that complexity doesn't create consciousness but organizes what was already there. The implications are staggering. If consciousness is universal, then the cosmos isn't a cold, empty machine, it's a living tapestry of experience. Trees might not think in words, but could they sense sunlight in ways we can't fathom? Could stars, in their nuclear hearts, harbor some alien form of sentience? Panpsychism doesn't just redefine life, it blurs the line between mind and matter, leaving us to wonder, if the universe is awake, what is it dreaming? Most conspiracy theories twist logic, but few bend time itself into a shape as bewildering as the time cube. Conceived by the late Jean Rey, this infamous idea claims that Earth doesn't experience a single 24-hour day, but 4 distinct days simultaneously, stacked together like layers of a cosmic sandwich. Picture a cube spinning on its axis. According to Rey, each corner represents a unique day unfolding at the same moment, with our linear perception trapping us in a lie fabricated by mainstream science. Rey's theory, which he called the greatest discovery in human history, emerged in the 1990s through rambling online manifestos and public lectures where he'd angrily brandish blue balls to symbolize Earth's 4-corner rotation. His central argument hinged on a bizarre reinterpretation of basic geometry. Just as a cube has 6 faces, 12 edges, and 8 corners, Rey insisted that time must have an identical structure, meaning dawn, noon, dusk, and midnight aren't phases of one day, but separate days coexisting in parallel. He accused scientists of suppressing this truth to maintain control, calling universities evil academic dungeons and dismissing Einstein's relativity as fraudulent. Scientifically, the time cube collapses under the slightest scrutiny. Time is a dimension, not an object with corners, and Earth rotation creates the illusion of a single solar day through its spherical shape, not cubic geometry. Yet the theory's cultural impact is undeniable. It became a hallmark of early internet eccentricity, a meme before memes existed, blending absurdity with a strange kind of poetic grandeur. Rey's rants, littered with phrases like "you're educated stupid," resonated with conspiracy circles precisely because they weaponized the incomprehensible, turning confusion into a badge of esoteric knowledge. What makes the time cube fascinating isn't its validity, but its reflection of how fringe ideas exploit gaps in public scientific literacy. Rey's insistence that gravity is a hoax or that children are born with 4 simultaneous brains reveals a pattern. When complex concepts like space-time are poorly understood, charlatans can repackage nonsense as forbidden truth. The theory also highlights the internet's role in amplifying extremism. Before algorithms curated outrage raise website, a wall of blinking text and animated GIF proved that even the most incoherent ideas could cultify if framed as rebellion against authority. Ultimately, the time cube is less about time than about human psychology. It's a Rorschach test for distrust, where the desire to feel enlightened outweighs the need for evidence. And while physicists rightly dismiss it as gibberish, its endurance as a cultural oddity begs a deeper question. In an age of misinformation, how do we separate playful speculation from dangerous delusion? The answer might lie not in debunking, but in understanding why some minds would rather shatter reality into cubes than accept the elegance of a spinning sphere. What if death isn't the end, but just a doorway to another version of you? Quantum immortality takes the mind-bending concepts of the many worlds interpretation and cranks them up to a chilling extreme. Imagine stepping in front of a bus only for the universe to split at the last possible instant, leaving a version of you unharmed in a timeline where the driver swerved, while another version, well, let's not dwell on that one. This isn't just speculative fiction. It's a fringe but mathematically coherent theory suggesting that consciousness might never experience its own extinction because there's always a branch where you survive. The thought experiment at the heart of this idea is called quantum suicide, devised by physicist Max Tegmark. Picture a modified gun pointed at your head, rigged to a device that measures the spin of a quantum particle. If the particle spins one way, the gun fires. If it spins the other, it doesn't. In the many worlds framework, every trigger pull splits reality. In some branches, you die instantly, but in others, the gun jams or misfires and you live. Here's the kicker: from your subjective perspective, you'd only ever experience the timelines where the gun fails. The other versions vanish from your awareness, like radio stations fading out as you drive past. You'd keep pulling the trigger, hearing nothing but clicks while countless alternates drop away. Critics call this solipsism with a quantum twist, a narcissistic fantasy where the universe conspires to keep you alive. But proponents argue it's just probability playing out. If infinite branches exist, there's no scenario where all versions of you perish simultaneously. Even in a nuclear apocalypse or heat death of the universe, there might always be one path where a lone observer clings to existence, a cosmic final survivor. The implications teeter between comforting and horrifying. If quantum immortality holds, aging might not be a march toward oblivion, but a narrowing corridor of increasingly improbable survivals. Picture a 120-year-old version of you, frail but alive, wondering why peers vanished decades ago, unaware they're thriving in branches where medicine advanced faster. It redefines mortality not as an endpoint but as a filter shuffling consciousness into increasingly rare realities. Yet the theory stumbles on the rocks of observable evidence. If countless near-death escapes happen, why don't we remember them? Why do we recall close calls, not absolute certainties? And if consciousness hops timelines, what stitches our memories into a coherent narrative? Perhaps the answer lies in quantum decoherence, the idea that branching worlds rapidly diverge beyond interaction, leaving no trace of the paths not taken. Quantum immortality doesn't just challenge our fear of death, it twists the knife on free will. If every choice spawns universes, are we really choosing or just riding a wave of infinite possibilities? And if you can't die, what does that make you? A prisoner of probability or the luckiest consciousness in the multiverse? The theory leaves us suspended between hope and existential dread, wondering if our survival is a miracle or just math. What if consciousness isn't just the result of neurons firing, but something far stranger, tiny quantum vibrations humming inside the very scaffolding of your brain cells? This is the radical heart of the Orch or theory, proposed by anesthesiologist Stuart Hameroff and physicist Roger Penrose. Unlike mainstream neuroscience, which treats consciousness as the byproduct of complex neural networks, their theory zooms into the microscopic world of microtubules, tiny protein structures that act as the skeleton of our cells. These hollow tubes found in every neuron might just be the universe's most sophisticated quantum computers, orchestrating consciousness at a scale smaller than atoms. The theory's name, orchestrated objective reduction, or hints at its two key ingredients. First, orchestrated refers to how these microtubules could coordinate quantum vibrations in perfect harmony, like a symphony of subatomic waves. Second, objective reduction borrows from Penrose's controversial idea that gravity causes quantum superpositions particles existing in multiple states at once to collapse, and that this collapse isn't random but a fundamental source of conscious experience. In simple terms, your thoughts might arise from quantum ripples collapsing inside microscopic tubes in your brain, with each collapse birthing a fleeting moment of awareness. Penrose's involvement gives the theory heavyweight credibility. His work on black holes and spacetime earned him a Nobel Prize, and he's long argued that quantum mechanics must play a role in consciousness. Hameroff, meanwhile, noticed something peculiar. General anesthesia, which switches off awareness, seems to target microtubules, freezing their quantum vibrations. If consciousness were purely electrical, why would these tiny structures matter so much? Together, they propose that anesthesia doesn't just silence neurons, it disrupts the quantum ballet inside them. But here's where the scientific gloves come off. Critics slam or as a quantum fairy tale, pointing out that the warm, wet environment of the brain should destroy fragile quantum states almost instantly. Nobel laureate Max Tegmark calculated that superpositions in microtubules would decohere lose their quantum magic faster than a snowflake melting in a furnace. Others argue that even if quantum effects exist in microtubules, linking them to consciousness is a giant leap without evidence. Why invoke quantum physics when good old-fashioned neuroscience explains so much? Supporters counter with tantalizing clues. Some studies suggest microtubules can sustain quantum vibrations longer than expected, shielded by their structure. Others highlight anomalies like near-death experiences, where brain activity flatlines yet vivid awareness persists. Maybe they speculate because quantum information lingers even when classical signals fade. The theory also dovetails with panpsychism, the idea that consciousness is universal, hinting that microtubules might tap into a deeper quantum layer of reality. The debate isn't just academic, it could redefine life, death, and everything in between. If or holds, artificial intelligence might never achieve true consciousness without replicating quantum processes. Anesthesia could become a tool to explore the quantum underpinnings of awareness. Even the soul, that age-old mystery, might find a scientific foothold in these vanishingly small vibrations. Whether proven or debunked, or forces us to ask, is the mind a mere machine or a quantum symphony playing in the hidden depths of our cells? Empty space isn't empty at all. It's a seething, writhing ocean of energy, vibrating with infinite potential. This is the zero-point field, a concept so strange it redefines what we call nothing. According to quantum physics, even in a perfect vacuum where every atom and particle has been removed, space still crackles with energy. Particles flicker in and out of existence so fast we can't catch them, borrowing energy from the future only to vanish again in a quantum game of hide and seek. These fluctuations aren't just theoretical, they've been measured, and their effects are real. They push on tiny objects in lab experiments, altering their paths. They might even hold the key to the universe's deepest mysteries, from dark energy to the nature of consciousness itself. But here's where things get wild. Some fringe theories suggest this zero-point energy isn't just background noise. It could be a cosmic hard drive, storing information in the fabric of spacetime. Think of it like ripples in a pond where every event, every thought, every moment leaves a tiny imprint in the quantum foam. Proponents of this idea argue that if we could tap into this field, we might access knowledge from across time and space, or even harness unlimited free energy. Inventor Nikola Tesla hinted at this possibility over a century ago, claiming to have discovered a way to draw power from the surrounding ether. Modern experiments with devices like the Casimir effect, where two metal plates placed nanometers apart in a vacuum are pushed together by quantum forces, show that zero-point energy can indeed influence the physical world. Skeptics dismiss the idea of extracting usable energy from the vacuum as pseudoscience, pointing to the laws of thermodynamics which forbid getting something from nothing. Yet the math behind zero-point fluctuations is rock solid, and their energy density is staggering. Some estimates suggest a single cubic centimeter of empty space contains enough energy to boil all the world's oceans. The catch, accessing it seems impossible without breaking physics as we know it. This hasn't stopped visionaries from dreaming. If the zero-point field does encode information, it could explain phenomena like intuition, déjà vu, or even collective consciousness patterns emerging from a shared quantum substrate. Some researchers speculate that our brains might interact with this field, acting as antennas tuned to frequencies beyond ordinary perception. It's a tantalizing thought. What if the whispers of genius, the flashes of insight, are just us brushing against the hidden data woven into the vacuum? Whether it's the key to free energy or simply a beautiful quirk of quantum mechanics, the zero-point field forces us to confront a humbling truth. The universe is far stranger than it appears. Even in the void, there is no true emptiness, only infinite potential waiting to be understood. Remember the children's book series about the lovable bear family? You'd swear it was called the Berenstain Bears with an E, but look closely at the cover now and you'll see it's always been Berenstain. This isn't just a typo or a trick of memory. For thousands of people, the E version feels viscerally real, as if their childhood reality has been quietly rewritten. This phenomenon, where large groups share identical false memories, is known as the Mandela Effect, named after the widespread belief that Nelson Mandela died in prison during the 1980s, despite him actually passing away in 2013. But why do so many remember events that never happened? And could this be more than just faulty neurons? Some theorists suggest the Mandela Effect might be evidence of parallel universes bleeding into our own. Imagine reality as a vast library where every decision spawns a new shelf of alternate timelines. Occasionally, the pages might get mixed up, allowing fragments of other versions to slip through. Those who recall the Berenstain Bears or the movie Shazam starring Sinbad, a film that doesn't exist, could be catching glimpses of branches where those things were real. Quantum physics even offers a loose framework for this. If the many worlds interpretation is correct and countless realities exist simultaneously, perhaps consciousness occasionally resonates with nearby timelines, creating these eerie overlaps. Skeptics counter with simpler explanations. Human memory is notoriously fallible, shaped by suggestion, and prone to filling gaps with plausible details. The brain often autocorrects words to fit familiar patterns, hence Berenstain morphing into the more Germanic-sounding Berenstein. Pop culture echoes amplify the effect. When one person misremembers the Monopoly man having a monocle he doesn't, others adopt the false memory through sheer repetition. Social media acts like a megaphone, turning quirks of recollection into viral conspiracy fuel. Yet some cases defy easy dismissal. Take Star Wars fans who vividly recall Darth Vader saying, "Luke, I am your father," when the actual line is, "No, I am your father." Or the hundreds who remember a cornucopia in the fruit of the Loom logo, despite no official record of it ever existing. These aren't vague discrepancies, they're specific, shared hallucinations, as if someone edited reality's source code and left behind traces. Whether glitch or psychology, the Mandela Effect taps into something primal, our fear that reality isn't as solid as it seems. It's one thing to misplace your keys, but what if you're misplacing history? And if enough people remember it differently, does that make their truth just as valid? The phenomenon doesn't just challenge memory, it forces us to ask whether the past is fixed at all, or if it flickers like a candle in the wind, reshaped by every observer who tries to pin it down. Terence McKenna's time wave zero isn't just a theory, it's a psychedelic roller coaster through history, claiming that time itself moves in fractal waves of novelty and habit, building toward an explosive crescendo he called the eschaton. Picture a cosmic countdown clock, its gears turning not in minutes or years but in layers of meaning, where every event, from the fall of Rome to the invention of the internet, fits into an ever-tightening spiral of significance. According to McKenna, this pattern wasn't random. It was mathematically encoded in an ancient Chinese divination system called the I Ching, which he mashed up with computer algorithms to pinpoint December 21, 2012 as the moment when time would essentially unravel. The allure of time wave zero lies in its audacity. McKenna, a self-styled psychedelic shaman, framed history as a kind of cosmic trip where societies rise and fall according to the ebb and flow of novelty, his term for complexity and unexpected change. As the waves grew tighter toward 2012, he predicted reality would hit a singularity of transformative chaos, a moment so dense with possibility that it might birth collective enlightenment or collapse civilization entirely. Sound familiar? That date, of course, overlapped with the Mayan calendar's much-hyped end, turning McKenna's fringe idea into New Age gospel. Thousands braced for dimensional shifts, alien contact, or at least a really wild party. Then the clock struck midnight and nothing happened. Critics rightfully shred time wave zero for its slippery math. McKenna's algorithm relied on cherry-picked historical events to fit his narrative, ignoring centuries that didn't align. The I Ching connection was tenuous at best, and his definition of novelty was so vague it could mean anything from the invention of agriculture to a viral cat video. Even fellow psychedelic advocates cringed at the pseudoscientific gloss coating what was essentially a poetic metaphor. Yet dismissing time wave zero outright, Mrs. Wyatt resonated. In a world drowning in data but starving for meaning, McKenna offered a story where history wasn't random but rhythmic, a grand fractal dance. His eschaton wasn't just doom, it was hope, a promise that human consciousness might leap forward. That narrative itch still lingers when quantum physics whispers about multiple timelines or simulation theory. It's tapping into the same hunger for patterns that McKenna exploited. The lesson here isn't about predicting the future. It's about the stories we tell to make chaos feel like destiny. Time wave zero may have fizzled, but its ghost lingers in every conspiracy theory that claims hidden order behind the noise. After all, if the universe is random, that's terrifying. But if it's a code waiting to be cracked, that's a trip worth taking. What if gravity isn't the universe's primary architect, but just a side character in an electric drama playing out across the cosmos? The electric universe theory throws conventional cosmology onto its head, arguing that electromagnetism, not gravity, holds the true keys to understanding everything from galaxy formation to solar storms. Mainstream science treats gravity as the cosmic puppeteer, shaping planets and stars with its invisible pull. But proponents like Wallace Thornhill and plasma physicist Anthony Peratt paint a different picture, one where swirling currents of charged particles sculpt the heavens and lightning bolts longer than galaxies flicker between stars. At the heart of this idea lies plasma cosmology, a framework where 99% of the visible universe isn't just gas and dust, but ionized plasma, a soupy sea of charged particles responding to electromagnetic forces. Picture neon signs on a cosmic scale. The same physics that makes a neon tube glow could explain the spiral arms of galaxies or the jagged filaments seen in nebulas. Thornhill's work suggests that when plasma moves through magnetic fields, it self-organizes into twisting ropes and double layers, forming structures eerily similar to those glimpsed by telescopes. Even the sun, he argues, might not be powered by nuclear fusion alone, but by electric currents flowing through space, a hypothesis that could rewrite how we understand solar flares and sunspots. The evidence: look no further than Jupiter's moon Io, where volcanoes erupt in perfect sync with electrical surges from the planet's magnetosphere, or comet tails, which mainstream models say are vaporized ice, but electric universe theorists claim are discharge phenomena, celestial lightning rods glowing under cosmic currents. Then there's the cosmic microwave background, often hailed as proof of the Big Bang. Plasma cosmology reinterprets it as the thermal echo of currents coursing through an eternal, unbounded universe. Skeptics dismiss these claims as fringe pseudoscience, pointing out that electromagnetism weakens rapidly with distance, unlike gravity. They argue that while plasma plays a role in local phenomena, it can't replace gravity's long-range dominance. Yet Electric Universe advocates counter with anomalies like galactic rotation curves, where stars orbit galaxies faster than gravity alone predicts, suggesting hidden electromagnetic forces at work. What's at stake isn't just academic debate. If the Electric Universe is real, it could revolutionize space travel, offering new propulsion methods harnessing cosmic currents. It might also explain mysterious events like the Tunguska explosion, not a meteorite, some suggest, but a gigantic plasma discharge. Most provocatively, it hints that the universe isn't a cold, mechanical clockwork, but a dynamic electrical tapestry, crackling with currents we've only begun to map. Whether groundbreaking science or overreach, the Electric Universe forces us to question which forces truly hold the cosmos together, and how much we still have left to discover. After all, if the stars are singing in electric whispers, what else have we failed to hear? What if an entire chunk of history never happened? The phantom time hypothesis claims exactly that, proposing that 300 years between the 6th and 9th centuries were fabricated, invented out of thin air by powerful figures manipulating the timeline. This isn't just a historical conspiracy, it's a full-scale rewriting of reality, suggesting that events like Charlemagne's reign or the rise of Islam might be elaborate fictions. The theory's architect, German historian Herbert Illig, argued in the 1990s that discrepancies in calendars, architectural styles, and astronomical records point to a grand deception, one that erased centuries overnight. Illig's case hinges on several bizarre anomalies. Take the Gregorian calendar reform of 1582, when Pope Gregory XIII supposedly corrected a drifting Julian calendar by removing 10 days. According to Illig's math, the accumulated error should have been 13 days, meaning 3 centuries worth of time might be missing. Then there's the eerie lack of archaeological evidence from this period in Europe, with some buildings and artifacts showing suspiciously uniform styles across what should be generations of change. Even celestial events get dragged into the mix. Records of solar eclipses from the so-called Dark Ages don't always align with NASA's modern retro calculations, hinting at possible tampering. But mainstream historians aren't buying it. They counter that Illig cherry-picks data while ignoring mountains of cross-referenced evidence, from Byzantine chronicles to Chinese astronomical logs that meticulously track the missing centuries. Carbon dating, tree ring analyses, and ice core samples all independently confirm an unbroken timeline. The Gregorian discrepancy, scholars attribute it to flawed calculations in early medieval Easter tables, not a global conspiracy. As for architecture, the uniformity Illig finds suspicious is easily explained by technological stagnation during Europe's post-Roman decline. The most damning rebuttal targets the theory's logistical absurdity. Fabricating 300 years would require collusion across continents, from Frankish kings to Abbasid caliphs, all somehow erasing births, deaths, and daily life without a trace. Yet no motive holds up. Why would the Holy Roman Emperor Otto III, whom Illig accused of orchestrating the fraud, bother backdating his reign to a fake past? Power grabs don't need imaginary timelines, they need armies and gold. Still, the phantom time hypothesis lingers in fringe circles because it taps into a deeper unease. How much of history is truly solid? We rely on fragile scrolls, biased chronicles, and fallible human memory. One fire at the Library of Alexandria, one forged document, and the past becomes malleable. While Illig's missing centuries crumble under scrutiny, his theory reminds us that history isn't just facts, it's the stories we agree to tell. And sometimes the most tantalizing stories are the ones that might not be true at all. What if reality isn't something we passively observe, but something we actively create? This is the radical premise of biocentrism, a theory championed by scientist Robert Lanza that flips our understanding of the universe on its head. Instead of treating consciousness as a happy accident in a pre-existing cosmos, biocentrism suggests life isn't just a passenger in the universe, it's the architect. Imagine the cosmos as a grand cosmic theater where the stage, the props, even the laws of physics don't exist until living observers step into the spotlight. This isn't mysticism, it's a bold fusion of quantum mechanics, biology, and philosophy, arguing that without life, reality as we know it wouldn't just be meaningless, it might not exist at all. Lanza's theory leans heavily on the eerie quirks of quantum physics, particularly the observer effect, the phenomenon where particles behave differently when measured, as if aware they're being watched. In classic experiments like the double slit, particles act like waves until a conscious observer checks the results, at which point they collapse into definite states. Biocentrism takes this further. What if the collapse isn't just a measurement glitch, but proof that reality requires a perceiver to solidify? In this view, a tree falling in the forest doesn't make a sound if no one's there, not because sound waves don't exist, but because the entire forest might not exist in a concrete way until consciousness interacts with it. The anthropic principle adds another layer. This idea, widely debated in cosmology, notes that the universe's constants, like the strength of gravity or the charge of an electron, are bizarrely fine-tuned to allow life. Tweak them even slightly and stars wouldn't form, molecules couldn't bond, and we wouldn't be here to wonder why. Mainstream science chalks this up to luck or a multiverse where countless universes with random constants exist, and we just happen to be in the one that works. But biocentrism offers a wilder alternative. What if the universe had to be this way because life is what defines it in the first place? Critics dismiss biocentrism as solipsism dressed in a lab coat. If reality depends on observers, they argue, how did the universe exist for billions of years before life evolved? Lanza counters with a twist. Time itself might be a construct of consciousness, a narrative our brains stitch together from sensory input. Just as a movie seems continuous despite being separate frames, the past could be a mental reconstruction, not an objective timeline. It's a dizzying thought. The Big Bang might not be a distant historical event, but a current process unfolding in the mind's eye. The implications are staggering. If biocentrism holds, death might not be an end but a shift in perspective, a departure from one reality into another. Near-death experiences where patients report vivid visions despite flatline brain activity could hint at consciousness persisting beyond the body's limits. Even the fabric of space might be malleable. Studies showing how human intention can subtly influence random number generators suggest the mind's reach could extend beyond the skull. Whether you find it inspiring or unsettling, biocentrism forces us to confront a fundamental question. Is the universe a cold, indifferent machine, or a living, responsive tapestry woven by the act of observation? The answer might not lie in telescopes or particle colliders, but in the very thing using them, the conscious mind peering into the void and finding itself staring back. What if the universe isn't made of matter or energy, but of information? digital physics turns this sci-fi sounding idea into a serious scientific framework, proposing that reality might be a vast computational system, humming along like the most sophisticated software ever written. At its core is a radical claim: the cosmos isn't just described by math. It is math running on a substrate of binary logic so fundamental that particles, forces, and even time itself could just be pixels in a cosmic simulation. The late physicist Edward Fredkin was one of digital physics' most outspoken pioneers. He argued that the universe operates like a cellular automaton, a grid of simple cells following basic rules where complexity emerges from countless tiny interactions. Think of it like a cosmic version of Conway's Game of Life, where the flickering patterns of living and dead cells create galaxies, atoms, and consciousness out of sheer algorithmic repetition. In Fredkin's view, the universe isn't just like a computer. It is one with space-time as its hardware and the laws of physics as its immutable code. This raises a jaw-dropping possibility. If reality is computational, then everything we experience, the taste of coffee, the sting of a wound, the glow of a sunset, might just be data being processed. Even quantum weirdness, where particles exist in multiple states until observed, could be the universe optimizing its processing load, rendering only what's needed, like a video game engine drawing graphics just within the player's view. Some theorists take this further, suggesting black holes could be cosmic garbage collectors, compressing information to free up memory, while the speed of light might be the system's processing limit, a cosmic frame rate preventing lag. But how could something as intangible as information create the solid world we touch? Consider water. At a distance, it looks like a smooth, continuous substance, but zoom in and it's a frenzy of discrete molecules. Digital physics suggests reality works the same way. What we perceive as smooth and analog might just be an illusion, a trick of scale hiding the universe's true pixelated nature. The math even checks out. Planck units, the smallest possible measurements of space and time, could represent the universe's native resolution, its fundamental bits. Critics push back hard. If the universe is a computer, they ask, who or what is the programmer? Digital physics sidesteps this by proposing the system might be self-contained, with no need for an external operator. Others argue that reducing consciousness to mere data processing feels cold and reductive. How can ones and zeros explain the warmth of a hug or the ache of grief? Yet supporters counter that emotions might be emergent properties, like a movie's emotional punch arising from colorless code. The most tantalizing clue might lie in the fabric of reality itself. Quantum entanglement, where particles instantly influence each other across vast distances, eerily resembles linked data packets updating in sync. Even the universe's obsession with symmetry, from snowflakes to galaxies, could reflect elegant coding principles. It's a humbling thought. The grand equations we've spent centuries uncovering might just be fragments of the universe's source code, waiting to be debugged. Whether poetry or programming, digital physics forces us to ask, if reality is a computation, what's the question it's trying to solve? We've all heard of black holes, cosmic vacuum cleaners whose gravity is so strong not even light can escape. But what if their opposites exist? White holes are one of the most tantalizing what-ifs in theoretical physics, behaving like black holes in reverse. Instead of sucking everything in, they violently spit matter and energy out, a cosmic fire hose blasting material into existence with no way back in. If black holes are the universe's drains, white holes could be its faucets, gushing forth new spacetime where nothing can enter. Einstein's equations actually allow for white holes just as easily as black ones, but for decades they were brushed off as mathematical oddities, until cosmologists started asking a wilder question. What if every black hole we see is secretly connected to a white hole somewhere else? This idea forms the heart of white hole cosmology, where the crushing singularity at a black hole's core doesn't lead to oblivion, but to a new universe bursting into being. Think of it like a cosmic Russian doll. Our universe might have been born from a white hole inside another universe's black hole, which itself could have originated from an even older cosmos. This gets stranger when you add wormholes to the mix. Some models suggest black and white holes could be two ends of the same tunnel, a bridge through space-time called an Einstein-Rosen bridge. Fall into a black hole here, and you might get vomited out of a white hole in another time or dimension. The catch, the forces involved would shred anything attempting the trip, at least in classical physics. Quantum mechanics offers a loophole. If information can escape black holes as Hawking radiation, perhaps it gets reprocessed into a new reality via a white hole, recycling the cosmos like an infinite cosmic printer. Time reversal adds another layer. Black holes warp time so severely that at their event horizons, clocks appear to freeze from an outside observer's view. White holes might reverse this effect, spewing matter from what looks like a reverse Big Bang. Some theorists even suggest that the singularity at the start of our universe wasn't a one-time event, but the white hole in point of a parent universe's collapse, meaning the Big Bang wasn't the beginning, just a rebirth. Critics argue white holes violate thermodynamics by creating energy from nothing, but supporters counter that they'd obey conservation laws if paired with black holes in a closed loop. Others point to fleeting gamma-ray burst explosions so powerful they outshine galaxies as potential white hole signatures, brief flashes of these cosmic geysers before they slam shut. Whether real or just beautiful math, white hole cosmology forces us to rethink the most fundamental question of all: where did everything come from? If the answer lies in the explosive exit of a white hole, then universes might not live or die, they just cycle, endlessly rewriting their own origins. Look closely at a fern's frond, and you'll notice each smaller leaf mirrors the shape of the whole. Zoom in on a snowflake, and intricate geometries repeat at tinier scales. Now stretch that idea across the cosmos. What if the universe itself operates this way, with the same patterns echoing from the vastest galactic superclusters down to the tiniest quantum vibrations? This is the fractal universe theory, a mesmerizing blend of mathematics and metaphysics suggesting that reality isn't just built on patterns, but is made of them, repeating infinitely like a cosmic hall of mirrors. The concept springs from the pioneering work of mathematician Benoit Mandelbrot, who coined the term fractal to describe shapes that display self-similarity structures where fragments resemble the whole, no matter how far you zoom in or out. His famous Mandelbrot set, generated by a deceptively simple equation, reveals endless complexity, spirals within spirals, jagged coastlines repeating into infinity. What's staggering is how these abstract mathematical ghosts appear everywhere in nature, in the branching of lungs, the swirl of hurricanes, even the distribution of galaxies across the void. Apply this to cosmology, and the implications are dizzying. The large-scale structure of the universe, with its vast filaments of galaxies threaded between empty voids, looks uncannily like a neural network in a human brain, or the branching veins of a leaf. Quantum foam, that seething chaos at the smallest scales, might churn with the same turbulent patterns as interstellar gas clouds. Some theorists take it further, proposing that black holes could be fractal seeds, birthing new universes with self-similar laws, a never-ending cascade of cosmic recursion. But fractals aren't just pretty pictures, they hint at something deeper. The universe's obsession with these patterns could mean reality operates like a mathematical algorithm, generating complexity from simple iterative rules. Think of it like a cosmic fingerprint. The same walls appear whether you're studying the distribution of matter in a galaxy cluster or the probability clouds of electrons orbiting an atom. Even time might be fractal, with events echoing across scales, histories rise and fall of empires mirroring the life cycles of stars. Critics argue this is more poetry than physics, that similarities across scales are coincidental, not evidence of a deeper unity. Yet the math keeps showing up. The way light scatters in nebulae follows fractal equations. The clustering of matter in the early universe aligns with recursive models. And if the universe truly is fractal, it could solve one of cosmology's biggest headaches: why the cosmos looks roughly the same in every direction yet isn't perfectly smooth. Fractal geometry naturally balances order and chaos, offering a blueprint for how complexity emerges without a top-down designer. Whether the universe is fundamentally fractal remains an open question, but the aesthetic pull is undeniable. There's something profoundly human in seeing our tiny lives reflected in the grand tapestry, like a cosmic whisper that we're part of a pattern far older and vaster than we can grasp. Perhaps fractals aren't just how the universe is, but how we're able to understand it, a language written in spirals and branching trees, waiting to be read. What if every choice you've ever made, every joy, every regret is destined to happen again, not just once but forever? The time loop universe theory takes the concept of déjà vu and cranks it to a cosmic scale, suggesting that time isn't a straight line but a closed circle, endlessly repeating like a broken record. This isn't just poetic musing, it's a chilling idea with roots in both philosophy and cutting-edge physics. Friedrich Nietzsche called it the eternal return, proposing that the universe cycles through identical versions of itself an infinite number of times. You've lived this exact life before, he argued, and you'll live it again down to the most trivial detail. The same breaths, the same heartbreaks, the same moment right now as you hear these words. Modern physics lends eerie credibility to this ancient intuition. Einstein's theory of general relativity allows for solutions where space-time curves back on itself, creating closed time-like curves, loops where cause and effect chase their own tails. Picture a river flowing in a perfect circle. Drop a leaf in and it'll float past the same point again and again. Black holes might be key here. Near their singularities, gravity warps time so severely that some models suggest particles could loop back into their own past, like a snake eating its tail. Quantum mechanics adds another layer. In experiments like the delayed choice quantum eraser, particles seem to retroactively change their behavior based on future measurements, as if time itself is a suggestion rather than a rule. But how would a time loop universe actually work? Imagine the cosmos as a vinyl record. We experience time as the needle moving forward, but the groove is circular. When the song ends, it starts over. Every supernova, every birth of a star, every thought in your head would replay with atom-for-atom precision. There's no escape, no deviation, just an endless rerun of existence. Some versions of this theory propose subtle variations, tiny quantum fluctuations that let each cycle differ slightly, but Nietzsche's original vision is stark, absolute repetition forever. The implications are paralyzing. If true, free will becomes an illusion. Your choices were predetermined the last time the universe reset, and they'll unfold identically next time. Even morality shifts under this weight. Nietzsche saw the eternal return as the ultimate test. If you knew you'd relive every moment endlessly, would you despair or find meaning in embracing the cycle? Critics, of course, point to entropy. The second law of thermodynamics states that disorder always increases, making exact repetition impossible. Yet some cosmologists speculate that in an infinitely expanding universe, quantum tunneling could reset entropy, allowing cycles to begin anew. Others argue that if time is truly circular, entropy itself might loop, resetting with each Big Bang. Whether a profound truth or a mind-bending thought experiment, the time loop universe forces us to confront the nature of time itself. Is it a river, a spiral, or a Möbius strip with only one side? And if we're trapped in a cosmic replay, does that make life futile or the most exquisite performance ever staged? What if the glue holding galaxies together isn't some invisible, mysterious substance, but something far more tangible, crackling with energy right before our eyes? The plasma universe theory flips modern cosmology on its head, tossing dark matter aside and arguing that electrified gas, not an unseen particle, sculpts the cosmos. At the heart of this radical idea is Hans Alfvén, the Swedish physicist who won a Nobel Prize for his work on magnetohydrodynamics, revealing how plasma, the fourth state of matter, can carry colossal currents across interstellar space. Forget dark matter's gravitational whispers. Alfvén's universe hums with electromagnetic forces, shaping galaxies with filaments of superheated, charged particles stretching millions of light-years. Plasma isn't rare. It's the universe's dominant material, making up nearly 99% of visible matter. From the shimmering auroras dancing over Earth's poles to the seething surface of the Sun, plasma's behavior is governed by electromagnetic forces far stronger than gravity at cosmic scales. Alfvén showed that when plasma moves through magnetic fields, it twists into rope-like structures called Birkeland currents, named after his predecessor Christian Birkeland. These cosmic power lines could explain galaxy rotation curves without invoking dark matter. Picture a spinning vinyl record. If you pour charged particles over it, their electromagnetic interactions create spiral arms and rotation speeds that mimic the effects of invisible mass. Mainstream cosmologists dismiss this, clinging to dark matter because it neatly fits their models, but plasma advocates point to stunning real-world evidence. The European Space Agency's Planck satellite mapped faint magnetic fields threading through galaxy clusters exactly where Alfvén predicted currents would lurk. Then there's the mysterious Great Attractor, a gravitational anomaly pulling our Milky Way toward it. Plasma cosmology reinterprets this as a massive electromagnetic focal point, a cosmic convergence zone for interstellar currents. Even the large-scale structure of the universe, with its vast web-like filaments of galaxies, mirrors the branching pattern seen in lab plasma experiments. The boldest extensions of Alfvén's work venture into wilder territory. Some theorists propose that plasma could generate life like self-organization, forming double layers that act as cosmic transistors, switching energy flows across the universe like a giant circuit board. Others suggest that quasars, those impossibly bright galactic cores, might be plasma-focused energy beams rather than black holes. And if plasma's electromagnetic forces dominate locally, could the Big Bang itself have been a titanic electrical discharge? Critics argue plasma can't replace dark matter entirely. It doesn't explain gravitational lensing or the cosmic microwave background's precise patterns. Yet the plasma universe's allure lies in its tangible nature. Dark matter remains a ghost hunted for decades without direct detection. Plasma, by contrast, crackles in every neon sign and lightning bolt, its behavior proven in labs and industrial applications. Maybe the universe isn't a gravity-driven machine, but a vast electric tapestry woven with currents we're only beginning to trace. Whether fringe or future mainstream, the plasma universe reminds us, sometimes the answers aren't hidden in the dark, they're glowing right in front of us. The holographic principle isn't just reshaping how we see the cosmos, it might also hold the key to unlocking the deepest mysteries of the human mind. Enter the holographic brain theory, a radical idea that suggests our memories, perceptions, and even consciousness itself could operate like interference patterns in a cosmic hologram. Neuroscientist Karl Pribram was the first to stitch together these seemingly disconnected threads, proposing that the brain doesn't store memories in specific cells or regions, but distributes them across its entire structure, much like a hologram encodes an image in every fragment of its film. Shatter a holographic plate, and any single shard can still reconstruct the whole picture, albeit fuzzier. Pribram argued the brain works the same way. Damage one area and memories don't vanish entirely. They just lose resolution, as if the mind is tracing echoes of a pattern woven into its very fabric. Pribram's inspiration came from an unlikely source, the baffling resilience of animal memories in mid-20th century experiments. Rats with surgically removed portions of their brains could still recall maze paths, defying the prevailing model that memories were localized. Meanwhile, physicist David Bohm was arguing that reality itself might be a holographic projection, with the universe's true nature hidden in a deeper, implicate order. Pribram fused these ideas, suggesting the brain might be a biological hologram, translating frequencies from a holographic reality into the vivid 3D world we perceive. Imagine your skull as a receiver tuning into a cosmic broadcast. What you experience as sight, sound, or touch could just be your brain decoding interference patterns from a deeper dimensional layer. This theory isn't without its skeptics. Mainstream neuroscience clings to the synaptic model, where memories form via strengthened connections between neurons. Critics argue Pribram's holographic analogy is just that, an analogy with no concrete mechanism for how neural networks could physically encode holographic data. Where's the biological equivalent of a laser or the interference patterns? Yet tantalizing clues persist. The brain's dendritic networks branch in fractal geometries eerily similar to interference waveforms. Even the placebo effect hints at something deeper. If belief alone can rewire pain perception or trigger physiological healing, could it be tweaking the holographic projection of the body itself? The implications spiral into the surreal. If the brain is holographic, then disorders like schizophrenia or déjà vu might not be malfunctions but glitches in the projection moments when the underlying code bleeds through. Near-death experiences could be the brain's attempt to render a reality beyond its usual bandwidth, like a radio picking up signals from a distant station. And if consciousness arises from this holographic process, then the self might not be anchored in the brain at all, but in the broader holographic field, with the brain merely acting as an interpreter. Pribram's theory straddles the line between genius and heresy, dismissed by some as poetic overreach while inspiring others to rethink the nature of perception. Whether the brain is truly a hologram or merely behaves like one, the idea forces us to confront a haunting possibility. The world we experience might not just be processed by the brain, but projected by it, a shimmering illusion woven from deeper, stranger threads. And if that's true, then reality, like a hologram, might be far more malleable than we've ever dared to imagine. What if our planet isn't just a rock teeming with life, but a living, breathing entity in its own right? The Gaia hypothesis, named after the ancient Greek Earth goddess, proposes exactly this. That Earth functions as a single, self-regulating superorganism, fine-tuning its atmosphere, temperature, and chemistry to sustain life like a body maintains its own homeostasis. Conceived by chemist James Lovelock and microbiologist Lynn Margulies in the 1970s, this radical idea shattered the conventional view of life as a passive passenger on a planetary stage. Instead, Gaia theory suggests life and environment co-evolve in an intimate dance, where bacteria, oceans, and even rocks collaborate in a grand cosmic balancing act. Lovelock's epiphany came while working for NASA, designing instruments to detect life on Mars. He realized Earth's atmosphere is wildly out of chemical equilibrium. Oxygen and methane coexist at levels that should react and vanish, yet they persist. The only explanation, life itself must be actively maintaining these conditions. Picture the planet as a giant terrarium. Forests act as lungs, oceans as circulatory systems, and microbes as invisible engineers, collectively stabilizing temperatures and gas mixtures over billions of years. When carbon dioxide rises and heats the planet, Gaia responds by spurring plant growth to absorb the excess. When oxygen levels climb too high, wildfires rein them back in. It's not conscious design, but an emergent intelligence woven into the fabric of life. But Gaia's scientific muscle is tangled with controversy. Mainstream biologists bristle at labeling Earth an organism, arguing it implies purpose where none exists. They see planetary regulation as a side effect of Darwinian competition. Species don't cooperate for Earth's sake. They selfishly adapt, and the system self-balances by accident. Lovelock's critics also pounce on his early computer models, which suggested Gaia could die, a metaphor they argue crosses into mystical territory. Even his allies, like Margulies, stressed that Gaia isn't a sentient deity but a metaphor for complex feedback loops. Yet the hypothesis found fervent adoption in New Age circles, where it morphed into something Lovelock never intended, a spiritual manifesto. Eco-activists framed Gaia as a conscious Mother Earth, punishing humanity's excesses with storms and extinctions. This mystified version drew eye rolls from scientists but resonated with a public hungry for harmony between ecology and spirituality. The irony: Lovelock, a staunch atheist, once joked that naming the theory after a goddess was his greatest mistake. Despite the backlash, Gaia's core insight, that life and planet shape each other, now underpins modern Earth system science. The discovery of the sulfur cycle, where ocean algae influence cloud formation, or the role of fungi in mineral weathering, all echo Lovelock's vision. Even climate change, often framed as Gaia's fever, reveals the fragility of these feedback loops. Push them too far, and the system tips into a new equilibrium, one less hospitable to us. Gaia forces a profound shift in perspective. We're not atop nature's hierarchy, but threads in its tapestry. Whether you see Earth as a machine, an organism, or something in between, the lesson is the same. Tug too hard on one thread, and the whole weave may unravel. Quantum mechanics paints a bizarre picture of reality at its smallest scales: particles existing in multiple places at once, cats that are both dead and alive, and a world that seems to dissolve into probabilities until someone looks. But here's the puzzle: if the quantum realm is so fuzzy and uncertain, why does our everyday world feel so solid and predictable? This is where quantum Darwinism steps in, a groundbreaking theory that bridges the gap between the strange quantum realm and the familiar classical world by applying a concept straight from biology: survival of the fittest. At the heart of this idea is physicist Wojciech, who proposed that the reason we perceive a single, stable reality isn't because quantum possibilities magically vanish. It's because certain states are better at replicating themselves, spreading their information through the environment like genes in an ecosystem. Think of it this way: when you measure a quantum particle, it's not just your interaction that matters. The particle's state leaves imprints everywhere, on the air molecules around it, the photons bouncing off it, even the table it's resting on. Some of these imprints are fragile and disappear quickly, like whispers in a storm. Others are robust, persisting and multiplying until they become the dominant story about the particle's state. These resilient imprints are what we perceive as objective reality. Jacques calls these surviving states pointer states, and they're the winners of a relentless information war. Just as natural selection favors organisms best adapted to their environment, quantum Darwinism suggests that only the most stable, redundant quantum states survive the constant bombardment of interactions with their surroundings. A lone photon striking an electron might not decide its fate, but trillions of photons interacting with it over time will reinforce certain states while others fade into obscurity. The result: the quantum weirdness we see in controlled lab experiments gets smoothed out into the dependable reality we experience every day. This isn't just abstract theorizing. Experiments with quantum systems show how decoherence, the process where quantum superposition breaks down due to environmental interference, aligns perfectly with Jacques' predictions. When atoms or photons become entangled with their surroundings, their delicate quantum states scatter information like confetti, but only certain configurations survive long enough to be observed. This explains why we never see Schrödinger's cat paradox in real life. The cat's macroscopic state is constantly being measured by its environment, forcing it into a definite condition long before a human opens the box. The implications ripple far beyond physics. If quantum Darwinism holds, then our perception of reality isn't just shaped by our own observations, but by a kind of natural selection operating at the atomic level. The universe isn't just a collection of particles, it's an information ecosystem where the most persistent data structures rise to the surface of our awareness. It even blurs the line between observer and observed. Instead of consciousness magically collapsing quantum states, the environment does the heavy lifting, with our brains simply tuning in to the most broadcasted signals. Critics argue that this still doesn't fully solve the measurement problem, why we perceive one outcome instead of another. But quantum Darwinism offers something rare in foundational physics, a testable pathway from the quantum to the classical. Future experiments probing the boundary between these realms could reveal whether Jacques' elegant idea holds the key to reality's hidden scaffolding. One thing's certain, in the battle for existence, even information must fight for its life. The universe is expanding, that much we know, but what if entire clusters of galaxies are being tugged towards something beyond the edge of our observable cosmos? This eerie phenomenon, dubbed dark flow, was first spotted by NASA astronomers in 2008, when they noticed hundreds of galaxy clusters drifting at staggering speeds toward a single patch of sky, as if drawn by an invisible hand. Unlike the uniform expansion driven by dark energy, this motion defies expectations, suggesting something massive, unimaginably massive, lies outside our cosmic horizon, warping the fabric of space-time with its gravity. The numbers are mind-bending. These galaxy clusters, some weighing trillions of suns, are racing at over 2 million miles per hour toward the constellations Centaurus and Vela. That's not just a slight deviation, it's a full-blown cosmic current, one that standard models can't explain. The leading hypothesis that the flow is evidence of other universes' realities beyond our own, exerting gravitational pull from regions we can't see. Imagine a rubber sheet stretched tight with marbles representing galaxy clusters. Now picture someone pressing a finger against the sheet far beyond its edge. The marbles roll toward the dent, oblivious to the source. Dark flow could be our first glimpse of that hidden finger. NASA Wilkinson Microwave Anisotropy Probe WMAP initially detected the anomaly by studying the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature shifts in this ancient light revealed the cluster's peculiar motion. Later, the Planck satellite confirmed the data, though with less intensity, fueling debates. Critics argue the signal might be statistical noise or local gravitational effects, like the Shapley supercluster, a colossal gathering of matter pulling nearby galaxies. But even accounting for known structures, the flow persists at scales that shouldn't be possible. The most radical interpretation ties dark flow to the multiverse. In some models of inflationary cosmology, our universe is one bubble in a froth of infinite bubbles, each with its own physics. If another bubble universe collided or brushed against ours long ago, the gravitational aftershocks could still be rippling through space, herding galaxies like cosmic sheep. Alternatively, dark flow might trace the gravitational imprint of a pre-Big Bang structure, a relic from a time before time, echoing into our epoch. Skeptics remain unconvinced. They point to potential instrumental errors or the challenges of measuring such subtle motions across billions of light years. Yet if dark flow is real, it rewrites the rules. Not only would it prove the cosmos extends far beyond what we can observe, but it might also offer the first tangible evidence that we're not alone in the multiverse. Until then, the mystery lingers. Are we seeing the shadow of another universe or just the limits of our own understanding? Either way, the cosmos just got a lot stranger. What if every time a rat learns a maze, rats everywhere find it slightly easier to solve? Or when a chemical crystal forms in one lab, the same crystal begins appearing more frequently worldwide? This is the radical premise of morphic resonance, a theory proposed by biologist Rupert Sheldrake that challenges one of science's deepest assumptions, the immutability of natural laws. Sheldrake's idea hinges on a startling claim that nature has a kind of collective memory, where patterns of behavior and form become easier to replicate over time, not through genetics or environment, but through an invisible field of accumulated habit. Picture a cosmic echo chamber where actions leave imprints, making similar future actions more probable, like grooves worn deeper into a record with each play. Sheldrake's inspiration came from puzzling biological observations. Why do some laboratory behaviors spread inexplicably between animal populations separated by continents? In the 1920s, Harvard psychologists found that once rats in London learned to escape a maze, new rats in Edinburgh seemed to master it faster, even with no genetic connection. Mainstream science dismissed this as flawed methodology, but Sheldrake saw something deeper. He argued that these morphic fields, non-physical organizing patterns, allow skills, instincts, and even physical structures to evolve not just through Darwinian selection, but through a kind of resonance across time and space. The more often a pattern occurs, the stronger its morphic field becomes, lowering the energy required for repetition. The implications ripple across disciplines. In chemistry, morphic resonance could explain why synthesizing new compounds often gets easier after the first successful attempt, a phenomenon chemists jokingly call the law of first synthesis. In human culture, it might clarify how fads or artistic styles emerge spontaneously across disconnected societies. Even individual learning could reflect this process. Sheldrake suggests that when you study a skill, you're not just rewiring your brain, you're tapping into a collective pool of knowledge shaped by every practitioner who came before you. Yet mainstream science has met morphic resonance with withering skepticism. Critics lambast it as pseudoscience for violating known physical laws, particularly the conservation of energy. How could information transfer across space and time without any detectable medium? Sheldrake counters that morphic fields aren't energy-based but informational, a distinction that leaves physicists unconvinced. Others attack his methodology, arguing his animal experiments lack rigorous controls to rule out sensory cues or genetic factors. The theory's association with parapsychology, Sheldrake has studied telepathy in pets and humans, further marginalizes it, branding it as New Age fluff rather than serious science. But beneath the controversy lies a profound philosophical rift. Sheldrake's work challenges the mechanistic worldview that nature operates like a clockwork of fixed laws. Instead, he proposes a universe where habits crystallize into laws, where the past actively shapes the present. It's a vision that resonates with ancient ideas, from Jung's collective unconscious to indigenous knowledge systems that see land and memory as intertwined. Whether morphic resonance is groundbreaking science or poetic metaphor, it forces us to ask, could the universe be less like a machine and more like a living thing learning as it grows? Ludwig Boltzmann's vision of the universe was as beautiful as it was unsettling, a cosmos where order doesn't come from design, but from the relentless churn of chaos. In the late 19th century, while others sought grand narratives or divine blueprints, Boltzmann wielded statistics like a sculptor's chisel, revealing how pockets of structure could spontaneously emerge from an ocean of disorder. His insight was simple yet revolutionary. Given enough time and enough particles, even the most improbable arrangements become inevitable. A gas might start as a swirling mess, but left alone, it will settle into equilibrium, not because it wants to, but because equilibrium is the most statistically likely state. Flip this idea to cosmic scales, and suddenly the universe's order, stars, planets, even life, might not be the product of intent, but a fleeting statistical fluke in an eternity of entropy. But here's the twist that still rattles physicists today. If Boltzmann's logic holds, then the universe we see, with its galaxies and laws, could just be one improbable bubble in an infinite sea of randomness. Worse, it suggests we might be living in the least likely version of reality. Think of a deck of cards shuffled endlessly. Most arrangements are chaotic, but once in a cosmic while, you'll get a perfectly ordered sequence. Boltzmann's nightmare that we're the ordered sequence and the vast majority of reality is a featureless void where no life, no stars, no time exists. It's like winning the lottery, only to realize you're the sole winner in a sea of losing tickets stretching to infinity. Modern cosmology collides with Boltzmann's universe in fascinating ways. Inflation theory, for instance, offers an escape hatch. By positing a rapid, early expansion of spacetime, it explains why our universe looks so orderly. It's a tiny patch smoothed out by inflation stretching. Yet even this doesn't fully dodge Boltzmann's shadow. Some versions of eternal inflation suggest our universe is just one bubble in a frothing multiverse, where most regions are cold, dead, and high entropy. The eerie conclusion, we might be the accident and the void the norm. Critics pounce on the theory's bleak implications. If Boltzmann's logic leads to Boltzmann branes, self-aware entities popping into existence from quantum fluctuations, why aren't we those branes, hallucinating reality instead of living in it? The answer might lie in cosmology's growing toolkit. The discovery of dark energy and the universe's accelerating expansion suggests a cosmic horizon, a cutoff point beyond which entropy can't spread. This could protect us from the statistical abyss, ensuring our universe's order isn't just a fleeting roll of the dice. Boltzmann's universe forces a humbling question: is our reality the rule or the exception? The answer might redefine not just our place in the cosmos, but the very nature of existence itself. Have you ever walked into a room and felt, for just a split second, like you'd stepped into the wrong version of reality? Or met someone who swears they remember historical events completely differently than the records show? These aren't just glitches in memory, they might be glimpses of something far stranger. The time slip phenomenon describes those eerie moments when individuals report suddenly experiencing or witnessing events from another time, as if the fabric of reality had briefly frayed, allowing them to peek through the threads of an alternate timeline. Take the infamous case of two British tourists visiting Versailles in 1901. Anne Moberly and Elena Jourdain insisted they'd wandered into the palace gardens only to find themselves transported to the late 18th century. They described encountering figures in period dress, including a woman sketching near the Petit Trianon who they later identified as Marie Antoinette. The details were vivid: the rustle of silk gowns, the absence of modern pathways, even the quality of the light feeling older. Skeptics dismissed it as an elaborate daydream, but both women were respected academics, and their accounts aligned perfectly despite being recorded separately. Then there's the baffling story of Lorena Garcia, a Spanish woman who woke up one morning in 2008 to find her life subtly but undeniably altered. Her longtime partner was gone, replaced by an ex-boyfriend she hadn't spoken to in years. Her job was the same, but at a different department. Even her pajamas weren't the ones she'd owned the night before. Garcia became convinced she'd slipped into a parallel reality, one where minor choices had branched into a drastically different present. Psychologists diagnosed her with a rare dissociative episode, but Garcia's insistence on the reality of her experience sparked fierce debate. Are these just tricks of the mind? Cognitive scientists point to conditions like déjà vu, false memory syndrome, or temporal lobe epilepsy as likely culprits. The brain is a master storyteller, stitching together perceptions and memories so seamlessly that we rarely question their accuracy. But time slip accounts often share uncanny consistencies: abrupt environmental shifts, a sense of static or pressure in the air, and details about historical periods the experiencers couldn't have known. In 1979, a couple driving through rural France claimed to have spent the night in a ghostly 19th century inn that vanished by morning, only to later identify it from a museum painting of a building demolished decades earlier. Quantum physics offers a speculative but tantalizing angle. If the many worlds interpretation is correct, with infinite parallel timelines branching from every decision, could brief overlaps occur? Some theorists propose that intense emotional states or geomagnetic anomalies might temporarily weaken the barriers between timelines, like a radio picking up cross-chatter from adjacent frequencies. Others suggest these could be mental projections, not literal time travel, but the subconscious mind accessing collective archetypes or morphic fields. Yet for every chilling account, there's a psychological explanation waiting in the wings. The human brain excels at pattern recognition even when none exist. Stress, sleep deprivation, or neurological quirks can manufacture vivid false memories. The Versailles tourists might have stumbled upon a historical reenactment. Garsh's story mirrors Capgra's delusion, where patients believe loved ones have been replaced by imposters. Even the most detailed time slips often crumble under scrutiny, like the man who swore he'd visited a 1950s diner that never existed, only to later realize he'd conflated a dream with a movie set. What's fascinating is how these stories reflect deeper anxieties about reality's stability. In an age of simulation theories and Mandela effects, time slips tap into our fear that the past isn't fixed, that history might be as malleable as memory. Whether neurological hiccups or genuine fractures in space-time, they force us to confront a haunting question. How much of our world is built on consensus, and how much is just one thread in a vast, tangled tapestry of might-have-beens? Imagine every moment of your life, every laugh, every heartbreak, every mundane coffee break spread out like frames on a film strip, all existing simultaneously. The past isn't gone, the future isn't unwritten, they're just coordinates on a map you're moving through. This is the block universe theory, a vision of reality where time is an illusion, and the cosmos is a static, four-dimensional tapestry woven from spacetime itself. Einstein's theory of relativity planted the seeds for this mind-bending idea. When he showed that time slows down for objects moving near light speed or in strong gravitational fields, he revealed time's flexibility not as a universal river flowing the same for everyone, but as a personal experience warped by motion and gravity. Think of the block universe like a DVD. The entire movie exists on the disc from start to finish, but the laser, your consciousness, only illuminates one scene at a time. Your now isn't special, it's just where the laser happens to be. This clashes violently with our instincts. We feel time passing, regret choices, dread the future. But in the block universe, your birth and your death are equally real, fixed points in the cosmic structure. The you reading this, the you as a child, the you taking your last breath, all eternally present like landmarks on a frozen landscape. Philosophers have wrestled with this for centuries. Presentists argue only the current moment exists, while eternalists embrace the block view. The debate heats up when you consider free will. If the future's already out there, are our choices illusions? Some physicists sidestep this by proposing that while all moments exist, causality still flows, like how a novel's ending is fixed but the characters don't know it yet. Others suggest consciousness itself might move through the block, creating the sensation of time. Einstein's equations treat time as a dimension no different than space, but our brains aren't wired to perceive it that way. Here's a paradox. If you could step outside the universe, you'd see every event: Caesar's murder, the birth of the first star, your next birthday laid out at once. Yet from inside, we're trapped in the narrow slice of now, blind to the whole. This isn't just abstract math. GPS satellites must account for time dilation, proof that relativity shapes our daily lives even if we can't feel it. The block universe forces us to confront the fragile nature of our experience. Is time's flow a trick of the mind, or is there something deeper it's trying to hide? Whether you find it liberating or suffocating, one thing's clear: the universe doesn't play by our clocks. It's all already written. We're just reading it one line at a time. From holographic projections and simulated realities to branching timelines and cosmic consciousness, these 30 theories don't just bend the rules of reality, they shatter them entirely. What's astonishing isn't just the diversity of ideas, but how each one, no matter how outlandish, forces us to confront the limits of human perception. Think about it, we're creatures evolved to survive on a single planet, yet we're peering into the abyss, asking questions that defy intuition. The universe doesn't owe us answers that feel comfortable or familiar. It might be a fractal tapestry, a quantum computation, or a reality so layered we've only scratched the surface. The beauty of these theories isn't in proving them right or wrong, it's in how they ignite curiosity. Every time someone challenges mainstream science with a wild idea like the electric universe or morphic resonance, even if it's debunked, it pushes us to refine our understanding. Remember, black holes were once dismissed as mathematical nonsense. Dark matter could be tomorrow's ether, or it might be the key to unlocking dimensions we can't yet see. The point isn't to settle on a single truth, but to keep questioning, testing, and marveling at how much we don't know. So here's your invitation: dive deeper. Pick a theory that makes your pulse race and dig into the research, the debates, the experiments that could prove or dismantle it. Maybe you're convinced we're living in a hologram, or perhaps your Team Boltzmann brain. Whatever resonates, share it below. Let's turn these comments into a collision of perspectives, because the next groundbreaking idea might start with a single "what if?" From someone like you. Reality is weirder than we think, and that's the most thrilling part.